So hello everyone, we are back to our plasma class, and in this class we will be dealing with the energy conservation equation that I promised in the last class. So we will be doing this in a bit a phenomenological manner rather than a concrete mathematical derivation. So we start that. So in plasma, inside plasma, you know that the plasma is a ionized gas consisting of these electrons and ions. So it can carry current, and this they are offering certain kind of conductivities, and they are colliding with each other, different particles, and they're colliding via long range Coulomb force. And because it is having this very high temperature, it can radiate. That is another additional thing. And of course you know that you can because these are associating atoms, ions, so you can change the internal energy of the system by exciting them, or doing some external work on that. So you see that here, what you are doing here, energy inside a plasma fluid basically governed by several mechanisms. Okay, so if we want to list one by one, as I have given here, the first one is work done by viscous stress inside the fluid. Now you know that viscosity. Viscosity is quite small in case of plasma, but it is not negligible in many of the processing plasmas. So you really have to consider the that viscosity and viscous dissipation inside plasma to accurately account for the energy balance inside the system. Viscous stress is nothing but the fluid friction. One layer trying to pass over the other layer, and they are imparting some force, and thereby they are basically doing work and generating the your frictional heating kind of thing inside the fluid. So that is how the viscous stress basically contributes to the energy equation, and we'll come to the exact expression for this viscous stress in our fluid model equations, where we'll be actually handling the practical systems. Then you know that whenever there is a gradient in temperature, then heat actually flows from one place to another, and the associated coefficient is your thermal conduction. So conductivity actually. So there heat can transfer from one place to another through thermal conduction as well, and plasma offers its own conductivity. Then when there is a temperature gradient, this particle, if move from one place to another, they're physically basically carrying the hot particles to cooler zone, and thereby carrying the energy on their own. So this is a kind of energy transfer, or which is physically being done by the particles, and that is occurring due to existence of the gradient. We'll come into details of that. The volumetric change of energy due to charged particles owing to temperature gradient, and then collisional exchange. You know that electrons are easily interacted by the electric field because of the lower mass of them. So they quickly pick up the energy from the field and accelerate and collide with the other particles. And thereby they impart their energy to the other species, and they make a change in the energy distribution, and this kind of contribution to the energy equation comes via collisional exchange of energy. Then you know that because plasma we have dealt many things like plasma conductivity. It may be high, it may be low, and many of the laboratory plasmas, they offer resistivity which is really substantial value, actually, which has substantial value. So in those cases, this plasma may be considered as a resistive element. So whenever current is flowing through that, then this J square by sigma term, J square by sigma term, that a ohmic heating term. So that will contribute to the Joule heating. Okay, and then there are certain reactions, exothermic reactions, which may happen inside plasma, because plasma species may well be chemically reactive. So whatever the energy that comes out from the reaction, they can contribute significantly to the plasma. For example, suppose you are oxidizing metals. So normally metals are there and oxygen is there, they will not react each other unless and until the temperature reaches some a very high value. And because plasma is a very high temperature object, so that temperature, that activation temperature is easily obtained. The moment the metal becomes metal oxide, it is usually becomes highly exothermic. So that heat that is coming from the reactions get added to the system, and that is some sort of volumetric heat generation. Now, volumetric heat loss due to radiation, it is important because plasma may have temperature beyond say 10,000, 20,000 degree Kelvin, and at that high temperature, sometimes the loss through radiation becomes really substantial, and we must account that properly. And many laboratories which are involved and which are continuously working to accurately estimate the radiation loss from different plasmas under different temperatures and operating conditions. So that is there. So radiation loss will be a part of the energy equation, and then the change in internal energy because of say excitation or de-excitation of the molecules. So those things will be there. So what we'll do, we'll go one by one for each of these kind of phenomena that may affect the energy equation. So first one is heat transfer through conduction. I start with this because this is a very familiar energy transport method which we are learning for long time. Now here you see that it is divergence of K grad T, the heat transfer through conduction. Now T is the temperature. When we are saying LT, I already explained in our previous classes that LT means that local thermodynamic equilibrium. So in such case, you have this electron temperature and ion temperature both are same. They are getting equilibrated through collision. Now this T then presents the temperature of the electrons as well as that of the ions, and K, whatever you are seeing over here, it is in case of plasma, it has components like your electron thermal conductivity, your atoms thermal conductivity, and ions thermal conductivity. And apart from that, you will know that there is something called reactive thermal conductivity. This happens when suppose you are considering oxygen plasma, and as you are increasing the temperature, is going up, and at certain temperature you will see that oxygen molecule is dissociating, and that way it is eating up the energy. So you are supplying energy and that is going somewhere, and so the phenomenon is happening because of the reaction. What is the reaction? Dissociation reactions. And the energy transport that is happening because of that, the conductivity, corresponding conductivity, we name as reactive thermal conductivity. So in plasma, if you plot the thermal conductivity as a function of temperature, then you will see that at certain temperature, like dissociation temperature, first ionization temperature, second ionization temperature, you will see a peak in the thermal conductivity. And those peaks are specifically contributed by the reactions like dissociation reaction, first ionization reaction, second ionization reaction, and these are appearing at only particular temperatures when where this kind of reaction get initiated, activated. Hmm. Now, other than that, at all temperatures, the contribution from the electrons or heavy species or the ions, they are always remaining there. So, over and above those conductivities, this conductivity, the reactive thermal conductivity, get added up at certain temperatures, where at specific temperatures where this kind of phenomena happens. So, let us go one real example here. What I have put, a molecular gas, and that gas is undergoing increase in the your temperature. So, you see one hump is over here and another hump is over here. And this one which is increasing like this dotted curve, this is the electron thermal conductivity which is increasing, and this one is for the your heavy particles, and then this is one which is for total, and you know this one, this is for heavy species, this is for reaction, this is the your dissociation reaction where this sump is there, this is the first ionization reaction where this sump is there, and you see this is the electron one and this is the heavy species one. So heavy species including the ions and the neutrals. And you know that in case of say laboratory plasmas like arc plasmas or RF produced plasmas, the degree of ionization at say when you are producing the plasma at normal atmospheric pressure, then the degree of ionization may be less than 0.1%, and so most of the gases remains unionized. So these are partially ionized gases, and majority of the gas is not ionized. So neutral plays an important role, and this conductivity includes the neutrals and the ions. And this one, this dotted one is the electron, and this one, this is basically a single curve. Huh? This hump is for your first ionization, and this is for dissociation. So this all get clubbed together, and you get a total thermal conductivity of this type. So remember that when we are modeling a plasma in fluid model, we basically need to understand the thermal conductivity in a very elaborate manner, considering all the species which are present over there and considering the reactions that may happen at different temperature. You know that these reactions, when the dissociation will take place, it will depend on the particular type of gas that you have used. For example, if I use oxygen and if I use nitrogen, this dissociation may be different, and similarly the ionization, the first ionization peak also may be different. So for every your plasma gas, this getting this curve is very much important, because the overall your energy balance mechanism will depend on the thermal conductivity, and thermal conductivity depends on all these parameters: what gas you are using, what are their reaction thermal conductivity, what is the electron thermal conductivity, more or less similar it will be having for your with temperature, this kind of behavior. But the heavy particle conductivity will depend on the kind of gas you are using, and of course the reactive thermal conductivity, these peaks will depend on the particular kind of gas that you are using. Now you know that rate of change of energy due to charge particle content. This has two parts. One thing is that due to ohmic heating. Okay. So rate of volumetric heat generation due to ohmic heating, that I write as U0, this one, and this one I write it as pi by 2 kb by E J dot grad T. Okay. Now this is basically a heat transfer which is due to this gradient of temperature and due to this J. Both of them has to be there to make this term effective. Okay. Now I am giving you one example, like suppose this room is hotter than the next room. Then those people who are staying in this room, they are equilibrated at the high temperature, and due to some call, maybe your friend is calling from the other room, you are moving. So that is basically constituting this J. So you are moving, though when the electrons are moving, then they are constituting this J. And when you are moving from this room to that room, what you are doing? You are carrying the high temperature from here to the other room. So physically, you are moving from this high temperature zone to low temperature zone, and then you are making that low temperature zone hotter. And why? Because of this J term existing there. So this is that kind of mechanism which is contributed as J dot gravity term. This is a very special term from plasma where it is carrying current and where the gradient in temperature is there. And you know that why this gradient in temperature should be there? This is mainly because you know that suppose you are passing a current through the plasma, basically that itself creates the plasma. So as you go further and further, heating continues. So initially, whatever temperature you may expect higher temperature at a downstream zone. That is how the your heating is taking place. So depending on the heating mechanism, some part will always be hotter and some part will be cooler. And because plasma is high temperature object, so to hold the plasma in laboratory or in some device, cooling is absolutely necessary. And when you are cooling, the part that this mechanical part which is holding the plasma, you must keep at a temperature which is lower than the melting point of the material that has been used for construction. So if that is the case, then you know that the plasma in touch of that will be in equilibrium with that, and that will definitely is going to be a low temperature plasma. But plasma you have created at a very high temperature, so that unit is at high temperature. So existence of some gradient in temperature is very common in plasma, and plasma unavoidably carries current. To sustain it, that is one thing, and if it is carrying current and if it is associated with the gradient in your temperature, then obviously this term is going to contribute. And this term is J is equal to sigma square. It is a very well known term. Sigma is the effective thermal conductivity that has been offered by the your plasma. And when you are multiplying by this electric field, so that is basically giving you the ohmic heating term. So this term will be there, and you can write this in terms of say current density as J square by sigma term. So this is the rate of change of energy due to charge particle content. You can see that both of them are related with charge particle. J is equal to sigma E. Sigma is the conductivity, and that is due to the charge particles, and then this sigma E square is the ohmic heating term. Now this one is the collisional exchange term inside the plasma. You know, we have told about that plasma is in equilibrium and plasma is not in equilibrium. So how this equilibration is happening? Because one fluid is colliding with the other fluid. The electrons are collide with the neutrals and ions, thereby they are imparting the energy they are having to the other species and trying to elevate the temperature of the other species. In that way, one species is gaining temperature and another species is losing temperature. A time may come when they are equilibrated. But when they are not in equilibrium condition, then their temperatures are different. So, you know that depending on the difference in temperature, they will be able to impart the energy. But if it is they have reached the equilibrium of LTE, that is T equal to TH, you know that this term will not be there. T equal to TH and this will be just 0. But as long as the equilibrium has not reached, the fluid is trying to reach an equilibrium, but if it is not reached, then this difference is there, and this collisional contribution will definitely contributing a lot in the energy transport equation. Okay, so this is the expression. Sigma is the collision cross section, you need to know that thing, and then VES, the relative speed between electrons and ions. Now you know that Ns is the density of the heavy species. So this is the kind of thing what you are having over here. Then you know that when this equilibrium has reached, then this exchange energy will be 0. Now how does this collision, volumetric collision frequency, okay, so number of collisions per unit time, that is the volumetric collision frequency per unit volume. So how many number of collisions are happening over there, and then per unit time. So that is what I have plotted over here. Just I use this one, and then here I tried to get the volumetric collision frequency, and I have plotted it over here for taking the data from actual working systems. And there I find that as you increase the temperature, then the collision increases. Then collision frequency reaches a maximum, and then they tries to fall down. This numbers you are seeing here. This is when T equal to TH, that is it is in equilibrium LT when T is twice the TH. That is electron temperature is more than the twice the more than heavy species temperature, almost double the heavy species temperature. Then when this is T by TH is 3, that is 3 times, and similarly this is for 20 times, this is for 30 times. So this is addressing a system where starting from the equilibrium LTE, it is ranging to a pretty amount of non-equilibrium, that T by TH is equal to 30. So what we see, say let us consider this T by TH is equal to 2, so electron temperature is twice the heavy species temperature. Then this curve is being followed. You just follow my cursor, then you will be able to see this is the curve that is being followed by that condition. Now why the volumetric collision frequency is very low at low temperature? This is because the temperature when it is low, the speed of the electrons is not high. So per unit time the path it crosses is low, and thereby whatever the colliding elements it find, it is not good enough. As the temperature increases, then it covers a much longer distance, and it becomes able to collide with number of particles, because temperature is increasing, so it is thermal velocity is increasing. So average thermal velocity increasing means it is being able to interact with more number of particles per second. So it is collision frequency is increasing. Collision frequency is nothing but the number of collisions per second. So it is able to collide with more number of particles per second, because it is now having a larger velocity. So that is how it is increasing. And now you remember that all this data, whatever we have put over here, is obtained for a particular pressure. Okay, pressure is constant here. Now when you are increasing the temperature very high, then what is happening? Because your pressure is constant, so volume is increasing, temperature is increasing, so PV equal to RT you can apply. So when your pressure is constant, V is proportional to T. Now when volume is increasing, when temperature is increasing, to keep the pressure, volume is increasing, then that number density itself is decreasing, because volume is increased. So number density when is decreased, then what is happening? Although the velocity of the electron is high, it is now not able to interact with many number of collision events. Actually, It is not able to make enough number of collision events, because with whom it will collide, that itself is less now. Number density is less because of the higher temperature, volume expanded, so density rarefied. So that is how the falling edge of the collision frequency appears. So you now understand, inside a plasma, depending on the kind of equilibrium or non-equilibrium, this volumetric collision frequency will vary, and you see that it has a strong impact on the non-equilibrium. So this collision frequency increases when the non-equilibrium increases, because non-equilibrium increases means that your electron temperature is high and then heavy species temperature is low. So that is how it behaves for the collision frequency. Now I come to the radiation loss. As I told you that plasma is a very high temperature object, and it is common that this plasma radiates very significantly. And you know that our sun is a plasma, and the radiation from it is almost like a black body. You know that Stephen Boltzmann law you apply for sigma T4 for black body radiation that we receive from sun. Now you know that for laboratory plasmas we are not handling that high temperature. So maybe say for example, if we are handling our plasma, that temperature, typical temperature is say around 8,000 to say 15,000 degree Kelvin, and of course its temperature can go up to 50,000 degree Kelvin depending on the kind of plasma that you have created, but typically the temperature remains say 10 to 15,000 degree Kelvin kind of thing. So there, whether the radiation loss is important or not, if we run the plasma at sufficiently lower current, then it may happen the temperature is less than 10,000 degree Kelvin, say maybe 7 to 9,000 degree Kelvin kind of thing. So whether at that temperature the radiation loss is important. Now what has been seen, this is the exact data in radiation watt per meter cube radiation loss, and at different temperatures for argon plasma. What we have plotted here, you see that below 10,000 degree Kelvin, the radiation loss is really insignificant. That as you increase the temperature beyond 10,000 degree Kelvin, the radiation loss increases almost exponentially. And at 20,000 or 25,000 degree Kelvin, the radiation loss becomes so huge that you must include this radiation loss term in your energy equation as a very important term. Okay, but you see that if you are using a processing plasma of argon less than 10,000 degree Kelvin, you can do a very realistic estimation if you even neglect the radiation loss. So we must be very much aware about the behavior of radiation loss with temperature to practically tackle the system, whatever the processing system you are having, in a very meaningful and in a very concrete manner. So you must know your system, what plasma it is, whether it is argon plasma, nitrogen plasma, oxygen plasma, or air plasma, and depending on the kind of plasma, your radiation property will vary. And we must have an exact idea about what is the radiation loss in watt per meter cube at a given temperature to understand the net energy balance equation. So that much is so far now, and in our next class actually we will try to explain how the steady state energy equation goes, and what are the different terms, and then we'll go for this numerical recipe about exactly handling the industrial plasma system. Okay, so we'll be back in our next class with the net steady state energy equation and the recipe for handling this complex set of equation and complete set of equation using numerical simulation. So I will just cursorily tell you the steps that is involved and give you some real life examples which has been tackled by numerical techniques solving the equations. So we will meet you in the next class. Thank you.